So we've seen that Ullmann's theorem is a very powerful theorem. It lets us decide when two bipartite states can be mapped from the one to the other by acting on only one of the systems on which the states are defined. So in this module, I just want to give you a couple words of caution about the theorem, giving on two different examples. So let's see. Let's first take a nice example. Let's consider these two states. The first is the usual EPR pair, 1 by root 2, 0, 0, plus 1 by root 2, 1, 1. Let's label these two qubits A and B. And the other state phi would be what's usually called the singlet, 1 by root 2, 0, 1, minus 1 by root 2, 1, 0. So these two states have the particularity that if I look at the reduced density matrix, on A, I get the identity, and on B also. Totally mixed state, half of the identity, and the same for phi. Let's call the reduced density sigma, half identity, and sigma B. So they have exactly the same reduced density matrices on both systems, but the states are very different. You can compute the inner product between psi and phi, and you get 0. So these two states are orthogonal, meaning they can be perfectly distinguished globally, but locally they look exactly the same. If you hold only the A system, whether it's the A system from psi or the A system for phi, you cannot tell the difference. The proof that you could not possibly tell the difference is given by Ullmann's theorem, which says that it's possible to go from psi to phi by acting on the B system only. So there is a unitary which acts on B only, maps the one to the other. This unitary is UB. How do we map psi to phi? We have to send 0 to 1 and 1 to, careful, minus 0. That's a unitary. And now what's interesting is that we can do the same by acting on A alone. We could have a unitary UA that again maps psi to phi. And what UA would do is that now we have to identify the other two states. So I need to map, when B is 0 in phi, I need to map 0 to minus 1 on A and 1 to 0. So if you look at what happens by applying UA tensored identity psi, you get phi, and you also get it by acting only on system B alone. That's quite an interesting property. Even more interesting now, you can check that if you actually apply UA tensored UB, both map at the same time, what happens to the state? Well, I'll let you check this as an exercise. Let's see another example now. Second example is one where things are not going to go so well. Let's try to apply Ullmann's theorem in the case where we have a tripartite system. So let's consider a state psi, which would be 1 by root 2, 0 on A, 0 on B, and let's have a C system now, 0 on C, plus 1 on A, 1 on B, and 1 on C. And let's have a state phi, which looks the same, except we do the same thing as we often do with the EPR pair. Let's write the same state in the Hadamard basis. So now I would put a plus, 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 and minus. Now these two states have the same property, essentially, as my states psi and phi, in the sense that all of their single qubit reduced density matrices are the totally mixed state, half of the identity, and here also. So they have the same single qubit reduced density matrices. Does it mean that I can map the one to the other by acting only on one of the systems? Is there a unitary UC that can map psi to phi? Now you have to think about it a little bit, but the answer is no. You have to be careful. The condition for being able to map psi to phi by acting only on system C would be that the reduced densities not on A or on B, but on A and B jointly should be the same. And here you can check that it's not the case. So if you compute the reduced density on A and B for the state psi, you get half 0, 0 plus half 1, 1. And for phi, you get density matrix sigma AB, which will be equal to half plus 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 half minus minus. And now these two reduced densities are not the same. For instance, you can check the overlap of the one and the other on 0, 0 and 1, 1, and you'll see that you don't get the same result. So these two are different, which means that the answer to the question here is no. So you have to be careful in trying to apply Ullmann's theorem to states that are more than bipartite, because it's really, if you want to see if the one state can be mapped to the other by acting on one system, the reduced density on all remaining systems should be the same. So it's very important that we talk about pure states here and not mixed states. I could have made a mistake by saying, look, let's look at the mixed state, psi, which is just the reduced density on A and C. And in that case, if I further look at the reduced density on A, they're the same in both cases. They're the totally mixed state. That doesn't mean that I can map the one to the other by acting only on C. So Ullmann's theorem only applies to pure states and not mixed states.